So continuing from yesterday, so yesterday we were talking about how to utilize this Laplace transform to characterize a linear time invariant system. Okay, so the idea is similar to that of Fourier transform because there is a unique representation of each impulse response with the Laplace transform. Therefore, certain properties of the impulse response, or let's say certain properties of the linear time invariant system, should be able to be represented, reflected in the form of the Laplace transform. Okay. So yesterday we started out with this causality. Right? We know that if a system is causal, then its impulse response can only be non-zero in the positive axis, meaning that it is a right-sided signal. Okay, so if the system is causal, its impulse response is right-sided, and therefore the region of convergence must be the right half plane. Okay. Now conversely, right? The converse is not, exactly true. Because if you know that the ROC is the right half plane, then you only know that the impulse response is right-sided. But a right-sided impulse response is not necessarily causal because it can start from a negative time. Okay? But if you know that the system is rational, meaning that it has a rational Laplace transform, then this converse holds. Right? So if the system is rational, then the ROC being the right half plane implies that the system is causal. Okay? So we do not have a proof for this here, but we look at it through a few examples. Okay. So first, we looked at this example here where we have an impulse response that is a one-sided decaying exponential on the positive axis. All right, so since this is non-zero only on the positive, only for t greater than 0, therefore the system is causal. And if you observe the Laplace transform, you'll see that the ROC is indeed the right half plane. Okay? And by the second statement here, right, because we're looking at a rational system, therefore, if you know that the ROC is the right half plane, which is the case here, then you can infer that it is causal. Okay. Now, in this second example here, the Laplace transform is also rational, but since you see that the ROC is not the right half plane, therefore you can infer that it is non-causal. Okay. So this equivalence holds only when your Laplace transform is a rational form, okay? If it's not a rational form, then this may not necessarily hold, okay? So this is what we want to see in this example here, okay? So in this example, you see that the ROC is the right half plane, okay? The ROC is the right half plane. Then you ask whether or not the system is causal. Okay. Now, if the Laplace transform is rational, then it would be true. But because the Laplace transform is not rational, there is this exponential on top. Therefore, we're not sure if it is true or not. Okay. So knowing that the ROC is the right half plane, we want to see if the system is causal or not. Right. All right. So knowing that the ROC is the right half plane, even if we are not sure if it's causal or not, but at least we're sure that the impulse response is right-sided. Okay. So the ROC is the right half plane. Okay, implies that h of t is right-sided. All right? Now, recall that this e to the minus t u of t has a Laplace transform that is 1 over s plus 1 with region of convergence greater than minus 1. Okay? So we know that this single-sided, right, one-sided decaying exponential has a Laplace transform that is 1 over s plus 1 with region of convergence greater than minus 1. Okay? Now this part is similar to this, except for this exponential term, right? But by the time-shifting property, we know that when we multiply a Laplace transform with e to the power s, this implies a time shift in the time domain. Okay? So if you recall, this is the time-shifting property, right? So if you multiply the Laplace transform by this exponential, then this implies a time shift of t naught, okay? All right. So by the time-shifting property, we know that this 1 over s plus 1 times e to the power s with the same region of convergence, right, this has a inverse Laplace transform that is a time shift by 1. Okay? So this e to the power s here corresponds to a time shift of 1. Okay. So the system, the impulse response corresponding to a system given here is equal to this. Okay. So hence, h of t is equal to e to the minus t plus 1 times u of t plus 1. Now, if you look at this signal is non-zero for t greater than minus 1. Okay? So this unit step function starts at minus 1. So if it starts at minus 1, then it is non-zero at certain time below time 0, meaning that the system is non-causal. Right? You have a response before the impulse comes in. Okay? So this system is non-causal. All right? So even though the region of convergence is the right half plane, it is actually non-causal, right? Because the system function is not rational. All right. So here we're mentioning these properties for a causal system. A causal system is a system that is non-zero only on the positive axis. Okay, so it is a right half plane. It has a right half plane region of convergence. Okay. Now, similarly, if you are looking at an anti-causal system, okay, if you're looking at an anti-causal system, which is a system with impulse response that is non-negative, that is non-zero only in the negative axis, right? So it's completely, opposite from a causal system, right? So in this case, h of t is equal to 0 for all t greater than 0, okay? So in this case, it is a left-sided signal, okay? And therefore, its region of convergence should be the left half plane, okay? So similar properties you can obtain for anti-causal systems, but instead of being on the right, the region of convergence should be on the left, okay? All right. Now, this causality is the first property here. Now, the second property we cover is stability, okay? So we say we can infer that an LTI system is stable if and only if the region of convergence includes the entire j omega axis, okay? So we can say that a system is stable if and only if it includes the entire j omega axis. So why is that? Okay. So having a region of convergence that includes the entire j omega axis means that the Fourier transform exists. Okay. So this means that the Fourier transform converges. Okay. Now, why is it that for a stable system, the Fourier transform must exist? Okay. Now, this is because for a system to be stable, its impulse response must be absolutely integrable. Okay. So for a system to be stable, its impulse response must be absolutely integrable. And if it's absolutely integrable, its Fourier transform exists. All right? So to check whether or not a linear time invariant system is stable from the Laplace transform, we can simply observe if the region of convergence includes the j omega axis or not. Okay? All right, so let's look at this example. So we have a system with Laplace transform with an algebraic form given by this. Okay. So you can, by partial fraction expansion, you can split this into 2 over 3, 1 over s plus 1, plus 1 over 3, 1 over s minus 2. Okay? So for this, we have 1, 0 at 1, a 0 at 1, and 2 poles at -1 and 2, right? -1 and 2. Okay? Now this is in rational form. So the region of convergence can have only 3 possibilities, right? One is either to the right of the rightmost pole. It can either be between these 2 poles, or it can be to the left of the leftmost pole. Okay? Now, which one of these are the actual, which one of these is the actual ROC may depend on different properties of the system. Okay? So for example, if we know that this system is causal, then we can infer that its region of convergence is this right half plane. Okay? So if the system is causal, okay, then the region of convergence is the right half plane okay? And this should be to the right of the rightmost pole. Okay? So if this is, if the overall region of convergence is to the right of the rightmost pole, then the region of convergence for this term should be, greater or equal to -1, and the region of convergence for this should be greater than 2, okay? Greater than -1 and greater than 2. And if you perform the inverse transform, this will give you a time domain impulse response that are both, decaying exponentials to the right. Oh, sorry. So this one's actually not decaying. So this is 2t ut. Okay? So, all right, because this is causal, we know that the overall ROC is the right half plane. Therefore, the ROC of both of these terms should also be the right half plane. So if you take the inverse transform, this will give you this single-sided exponential, and this will give you this single-sided exponential. Okay? Now you can see here that the exponent here is positive. Okay? The exponent here is positive. So as t goes to infinity, actually this thing blows up to infinity. Okay? So the system is actually not stable. Right, the system is not stable. And you could have also observed this directly from the ROC, because you can see here that the ROC does not include the j omega axis. Okay? Okay. Now we can look at, other possibilities. Right, so here we inferred that the impulse response is this by the fact that the system is causal. Okay. Now suppose that instead of knowing that the system is causal, suppose you know that the system is stable. Okay. So if the system is stable, then you know that the region of convergence must include the j omega axis. Then the only possibility is when the ROC is this strip in between. Okay. So if the system is stable, okay, then the ROC must include the j omega axis. Okay? Or in other words, it is the region corresponding to the real part of S being greater than -1 and less than 2. Okay. All right. So by the fact that the system is stable, we know that the ROC is this strip here. Okay. So the ROC is to the right of -1 and to the left of 2. Okay. So therefore, we know that when you split it into these two terms, this term should have an ROC that is the right half plane, and this should have an ROC that is the left half plane. Okay. So this will, inverse transform to a right-sided signal, and this will inverse transform to a left-sided signal. Okay. So by that, you will get an impulse response That's 2 over 3 e to the minus t u of t, right, for the first term, which is a right-sided signal. And for the second term, you have minus 1 over 3 e to the 2t u of minus t. Okay. Now, why is this system stable, right? So we inferred that the system is stable by observing its ROC, which includes the j omega axis. But if you look at the time domain, right, what it has is a one-sided decaying exponential to the right, okay? And then in the second term, even though we have a, this 2t in the exponent, but because t is, right, here we have a unit step function that is non-zero only to the left of the origin. So the t here must be negative, right? So as t goes to minus infinity, this exponential actually is also decaying, okay? So one decaying to the right, one decaying to the left. So overall, it is absolutely integrable, okay? All right, so the last one, okay, so for this one, we know that if the system is causal, the impulse response is this. If the system is stable, we know the ROC is this, and therefore the impulse response is this. Now, suppose you know that the system is anti-causal, okay? Okay? So if it is anti-causal, then it must be the left half plane. And therefore, if you look at this expansion here, both of these terms should have an ROC that is the left half plane. So the overall response is a left-sided signal, okay? So we get minus 2 over 3 e to the minus t minus 1 over 3 e to the 2t u of minus t. Okay? Now notice that this is also unstable. Okay? This is also unstable because this first term now blows up as t goes to minus infinity. Okay? And you can also see that from the ROC because the ROC does not include the j omega axis. Okay. Right. Now, if you're looking at a rational system, okay, we know that the region of convergence must extend all the way to its pole, okay? So the region of convergence of a rational system can either go to infinity or be bounded by its pole, okay? So for a causal system to be stable, okay, this means that all of the poles of H of S must lie in the left half of this S-plane. Okay. So suppose you have something like this. Okay. So if you have poles, let's say, here, then you're right. Then for a causal system, okay, its region of convergence must be here. Okay? So if you have any poles to the right of the origin, then it's impossible for the ROC to include the j omega axis, and therefore the system cannot be stable. Okay? So if you want a system to be stable, you must design a system where all the poles are in the left half of the S-plane. So this is the only way for you to have a ROC that includes this J omega axis. Okay? Okay. All right, so we can look at a couple of examples. So here we have a causal system with impulse response given by this, okay? So this is a one-sided decaying exponential. It's absolutely integrable, right? And it has a Laplace transform that is rational, right? Because in fact, the Laplace transform in this case is 1 over s plus 1. And because it's causal, its region of convergence is greater than minus 1, right? So you can see here that this system is indeed stable because its pole is in the negative plane, right? In the left half of the S-plane. Okay. Now, suppose you consider a causal system with impulse response given by this. Right? So this is a increasing exponential to the right of the origin. Okay. Now, if you observe the Laplace transform, this is 1 over s minus 2. And because it's causal, the region of convergence must be greater than 2. Okay? But in this case, the pole is at 2, so the region of convergence is to the right of 2, which does not include the j omega axis, and therefore it is unstable. Okay? So you see here that the pole is in the right half of S-plane. Okay? And therefore, it's unstable. Okay? All right, so this is another example we've seen earlier, right, for a second order system. So, right, if you work through the derivations, which we did in an earlier chapter, you will see that there are two poles, one at C1 and one at C2, which is given by this. Okay? So basically, if you have a zeta that is negative, right? If you have a zeta that is negative, then you will see that both C1 and C2 will lie to the right, on the right half of the S-plane, right? So for example, these 2 points here. And therefore, for such a causal system, it cannot be stable because it cannot include the j omega axis. Okay? So this is the case for zeta less than 0. Okay. So this equivalence is only for rational systems, right? Systems with rational Laplace transform.